Okay, this is the seventh video in the kinematics section, and it's about projectiles. So projectiles are, as it says here, a form of vector kinematics that model the projection of an object under the effect of gravity. And the acceleration is going to be the effect of gravity. The acceleration due to gravity is constant, and therefore we can use our Subat equations, and we're kind of using them in two directions. So here's a sort of and I should say that that's a vertical acceleration. There's invariably no acceleration in the horizontal direction. Here's a sort of problem that we get. You know, here's a boy on the top of a cliff building or something, and then he kicks this football, and he kicks it sort of up at an angle. So we know we're given in this problem here what the angle is and what the actual speed, the scalar, the ball starts off at. And the problem is to actually work out how far it travels from the base of this cliff. So it's the horizontal distance of travel. So the sort of classic form of this problem involves looking at the up-down motion in order to work out the time that the ball is in the air, and then using the horizontal, or then using that in the horizontal travel to work out the distance. Now, not all the problems are like that. That's a very typical form. Everything else is, you know, sort of kind of related, really, but there are, you know, obviously not always being asked for the horizontal distance. One important thing is this is really where the difference between displacement and distance comes in and works, largely speaking, to our benefit. Because when we're looking at the vertical motion, we're interested in displacement. So the displacement here would be, assuming we've got our positive is upwards, then our displacement would be negative of this. That's the displacement. So the fact that the ball starts going up and then comes back down again kind of drops out of our displacement equation. We're just interested in the overall displacement. That's what that equation gives us. So that is something that kind of works for us, really. Just have a look at this statement here. Boy kicks the ball from the top of a 40-meter high cliff at a speed of 20 meters per second. That's an angle of 30 degrees to the horizontal. How far does the ball travel horizontally until it hits the ground, taking g equals 10 meters per second? It should be. Okay, so this is, to illustrate, this is the sort of that classic form of the problem in my terms. Using this notation here to denote the fact that we're initially looking at the up-down direction. So displacement equals ut plus half at squared. That's the kinematics equation. So the displacement is minus 40. So upwards is our positive direction, where the ball ends up going downwards, so it's minus 40. The initial velocity, 20 sine 30. So it's that direction there. Okay, so 20, and then it with the sine of this angle, cosine of that angle, but of course that's the same as sine of 30, times t plus a half times a. Now again, our positive direction is upwards, so acceleration due to gravity is downward, so that would be minus 10 t squared. So if we just kind of evaluate that, we get this equation rearranging, we get this, which is the same as that, t squared minus 2t minus 8 equals 0. We can factorize this, and we get we get this factorization, t minus 4, t plus 2. So that's actually, there are two solutions to that simultaneous equation. That's 4 and minus 2. In this particular problem, we're not really interested in anything prior to t equals 0. So whilst that gives us a solution, t equals minus 2 for this equation, it's not a solution for this particular problem. So the solution for this particular problem is just this t equals 4 seconds. So this ball is in the air for 4 seconds. Now, thinking about the horizontal, then we've got pretty straightforward Suvat equation. S equals vt. There's no acceleration involved. So the horizontal velocity is 20 cos 30. This is 20 resolved through this 30 degrees here, times the time. Cos 30 is root 3 over 2. So when we multiply that through, then we just get 40 root through 3 meters, about 68 meters or something like that. So that is how that works. So that just kind of illustrates this very sort of a simple example. Now I've got a couple more to illustrate how it works, and that hopefully will help to explain it all. A golf ball is struck from a point O with velocity 24 meters per second at an angle of 40 degrees to the horizontal. The ball first hits the ground at point P, which is a height h meters above the level of O. It's probably hitting it onto a raised green. And the horizontal distance between O and P is 57 meters. Yeah. Show that the time that the ball takes to travel from O to P is 3.10 seconds, correct to 3 significant figures. Okay, so yeah, 57 meters. So this is just a horizontal thing. So this part A, we're actually only interested in the horizontal travel. We know the velocity. And we know the distance. So really it's just S equals VT. And in fact, if we plug S in there, V equals this, it's 24 cos, resolving through 40 degrees. T we don't know, so that's our equation. Plug those things in there, work it out, and that's what we get. T equals 3.10 seconds. And probably should have put in brackets to get 3 significant figures. This goes on to say find the value of h. Right, now we're a bit more interested in the vertical travel. And when we look at that, I mean, we tend to use this equation in the vertical all the time. I mean, it's kind of if you're not using this equation to look at vertical travel, then it's an unusual question. It's not impossible, but you can pretty well expect that this is going to come in for your vertical travel. So we got S equals ut plus half at squared. And now S is S is h. So because it's starting off from the ground, so the net distance that it's going up is h. Okay. So, and that is going to be equal to the initial velocity in the vertical direction, 24 sine 40, times the time of travel, 3.10, plus a half a, that's acceleration, it's upwards acceleration, which of course is negative, times 3.10 squared. And yeah, so we know, all these are just, this is just a calculation, put that in your calculator, and it will give you 0.734 meters to 3 significant figures. Good. Okay, that's okay. Part C, find the speed with which the ball hits the ground. Now, I put the arrow in to illustrate here, because speed is a vector in these kind of questions. it really means that we're looking at the magnitude of the velocity. So we need to know the vertical and the horizontal. So we need to know it as basically as a vector, and then to use Pythagoras. So if we're looking at the up-down direction, v equals u plus at. Well, that's okay. So this is resolving our vertical velocity, the vertical part coming down here. We know the initial, this is 24 sine 40, as we had before. So this velocity resolved upwards. Plus a, well, our positive direction's upwards, so g is, so our acceleration is minus 9.8 times the time. And essentially that's going to give us a velocity. This is a velocity of minus 15. Why is it minus? Why is it minus? Well, because our frame of reference is upwards, and it's coming downwards. So it's going to be minus 15. And had it been positive, we probably would have made a mistake. So so we know that. We do also know the horizontal part of this, because it's the velocity it started off with. It doesn't change. There's nothing. There's no other forces. We're assuming there's no wind air resistance in all this, or wind or anything else. So it's basically the velocity with which it started, which is 18.39. I think we've done that offline. That is basically your 24 cos 40. So if we just draw this in a little triangle of velocities, 18.39, 14.96, and we just calculate that angle there, it gives us 39.12 degrees. And that's it. You're just missing here. Actually, we should, if we needed to find the speed with which the ball hits the ground, so that would have been applying Pythagoras to this and this. So it would be the square root of this squared plus this squared, and that would have been your the speed at which it hits the ground. Okay, so yeah, that's a nice little problem. Sorry, let's get this. Right, so let's have a look at this one. A pretty similar sort of thing, really. Particle P is projected from the point A, which has position vector 47.5j, with respect to fixed origin at O. Velocity of projection is 2ui plus 5uj. Particle moves freely under gravity, passing through B with a position vector 30i, 30 meters, as shown. Show that the time taken for P to move from A to B is 5 seconds. Okay, so a couple of things here is that we're first of all, obviously, it's described in vector terms. You don't really need the vectors, do we? And we've seen on the previous example, it's, we can talk about horizontal distances, vertical distances. So why is it written as a vector? Really need it to be vector. But if they ask it in a vector form, and they want a vector for an answer, you need to express it in those terms. Okay, let's have a look and see what we're doing. Yeah, so the time taken is pretty well always determined by the vertical travel, as it is here. So S equals ut plus half at squared. Yeah, so the displacement, well, the displacement was going to be negative, isn't it? Because it's going downwards. The net effect is going downwards. Our frame of reference is upwards. Minus 47.5 equals 5 ut. Yeah, we've got, this is our standard equation. So this u here is sort of a different u to this one. This is where we've got to be a little bit careful. I've mentioned in the SUVAT video that sometimes our letters get hijacked for other meanings in the problems. So I could have written V0 there just to make a distinction, but no matter, we can cope with that. So so we get our 5u from here. Okay, time to time minus a half g t squared. Well, I put minus because g is a positive constant, but of course it's acting in the different direction to our frame of reference. So that's how we get the negative. So that is our equation that we're interested in the vertical. Where are we going on this one? So if we look at the horizontal, S equals VT. The horizontal distance 30 is equal to 2u, which is this, times t, meaning ut equals 15. Okay, so we've had to look at this horizontal because, to be honest, we couldn't otherwise solve this for t. But now that we know that ut equals 15, we can substitute that into there, and then we've got this equation here, which gives us an equation in t squared, which we can solve for t equals 5. Okay, so this is a slightly tricky little thing that you need to be able to spot this, because if you just looked at this and go, well, what am I going to do now? Don't know, but it is an example actually of simultaneous equations, isn't it? In we're using two orthogonal directions to give us simultaneous equations. So we've not really expressed it like simultaneous equations, but that's essentially what we're doing. Okay, so that gives us t equals 5. So I hope that's clear. If not, you can rewind the video and perhaps go over it again. The value of u, well, now we know we can go back to this equation. 30 equals 2u times time, which is 5. That's just equation in u, so that gives us u equals 3. That's straightforward, I think. And then find the speed of b at p at b. So again, this is a similar one. It's the speed. We're actually looking at the actual speed along this direction. To the tangent, isn't it? Because there's a curve. So the vertical velocity at b is given by v equals u plus at. This is similar to before. Minus 5u. Well, our u from our equation is actually implemented as 5u here. Okay. Except, of course, our frame of reference is in the opposite direction. So 5u plus gt. So we've got minus 5 times u, which we know to be 3, plus 10. We're taking g as 10 in this problem. Times 5, and that's going to give us v equals 35. So from that, without going through all the details, well, we know the horizontal velocity because that's given to us there, 6, and therefore we're basically just going to use Pythagoras on the vertical and horizontal velocities to give us the speed at b. So kind of all right. So kind of shot through that last bit, but that's very similar to what we did before. So okay, so that basically is a bit of a run through on how we do projectiles problems, and so hopefully that's been useful, and thank you for watching.